Welcome to the Sleepy Scholar. It's lovely to have you here. Wherever you are tonight, whatever corner of the world you've folded yourself into, I'm glad you came. Maybe you're under a heavy blanket with the weight of it pressing you gently down into the mattress. Maybe there's a lamp still on across the room, throwing a soft, warm circle of light onto the wall, the kind you keep meaning to turn off but somehow never do.
Maybe you're on a couch with one leg hanging off the edge, or on a train with your head against the cold window, or in a bed that isn't yours, in a city you're only passing through. It doesn't matter where. You found your way here, and that's enough.
So before we begin, let me ask you the only question I'll ask all night that has a real answer. Where in the world are you watching from? What time is it in your corner of the dark? I always wonder. Somewhere out there it's the middle of a long afternoon and you've drawn the curtains to fake the night. Somewhere else it's 3 in the morning and your mind simply will not switch off. Tell me, if you like, down below. It costs nothing, and I do read them in the quiet hours, imagining all of you scattered across the turning planet, all listening to the same slow voice. And while you're down there, if these slow journeys help you drift off, a like and a subscribe really does help this sleepy little channel keep going. I know it's a small thing to ask, but small creators like me genuinely rely on it, on you, on the gentle tap of a button before you fade. And to those of you already subscribed, already here, night after night, thank you. Truly. You're the reason there's another video at all. Now, settle in. Get comfortable. You don't have to hold any of this. You don't have to remember a single number I say. If you drift off before the end, that's perfectly fine. The galaxy will still be here when you wake. It's been here a very long time. It can wait. I'll try, as I always do, not to make this so interesting that it keeps you awake. Though I'll admit, tonight that might be hard, because the thing we're going to talk about is so large, so strangely empty, so much stranger than the pictures make it look, that it has a way of quieting the mind all on its own. But if it does keep you up, well, at least you'll have learned something, a fair trade, I think. Tonight, we're going to take a journey, a long, slow one, with no rush at all. We're going to travel across our galaxy, the Milky Way. From its very center, where something enormous and silent sits in the dark, all the way out to the last star, where the galaxy doesn't so much end as simply fade, like a breath dissolving in cold air. We'll pass the central bar, the great spiral arms, the dim, crowded heart, and the lonely outer edges. We'll find the exact spot where you are right now on this small, warm world, and we'll try together to feel, not just to know, but to actually feel how big it really is. But here's the thing about size. Numbers don't do it. If I tell you the galaxy is 100,000 light years across, that means nothing. It's just a sound, a big sound, but a sound. Your mind hears it and slides right off, the way your hand slides off wet glass. So we're not going to do that tonight. Instead, we're going to build a model, a little scale model in our heads that will carry with us the whole way, and we're going to build it honestly. Because most people who talk about the galaxy make it sound crowded and bright and full, and it isn't. The truth is gentler and lonelier and far more beautiful than that. Let me show you. Let's start with the sun, our sun, the one that warmed your skin today, or yesterday, whenever you last stood in it. It feels enormous, doesn't it? It dominates the sky. You can't even look at it. And it is enormous by our small standards. The sun is about 1.39 million kilometers across, 1,390,000 kilometers from one side to the other. You could line up more than 100 Earths across its face and still have room. It is, by any human measure, a giant, a ball of fire so vast we can't really picture it either. So let's shrink it. Let's take that sun, that 1.39 million kilometer ball of fire, and let's squeeze it down gently in our minds until it's the size of a single grain of fine sand, the kind you'd find on a quiet beach, so small it sticks to your fingertip and you can barely brush it off. About 0.5 millimeter across. Smaller than this, the sun, smaller than a grain of sand on the tip of your finger. Can you hold that? Good. Keep it there. Now, to shrink something that big down to something that small, we had to do something almost violent to it. We shrank it by a factor of, and I'll say this number once, slowly, and then we'll never need it again. About 2.8, with 15 zeros after it. 2.8 quadrillion. That's how many times smaller our grain of sand sun is than the real one. It's a number too big to feel, which is exactly the point. We needed a number that big just to make the sun small enough to hold. So now here's the magic of it. Whatever we do to the sun, we have to do to everything else. That's the only rule of a fair-scale model. If the sun shrinks by that factor, then so does the galaxy. So let's take the whole Milky Way on that 100,000 light-year disk and shrink it by exactly the same amount. And let's see how big our model galaxy turns out to be. Now, 100,000 light-years, written out in kilometers, is a truly absurd number. It's about 950,000 billion kilometers. There's no point even trying to feel that one. But that's fine. We don't have to. We just have to shrink it. So we take that monstrous distance and we squeeze it down by the same 2.8 quadrillion factor. The same shrink we did to the sun. And what do we get? We get a disk about 340,000 kilometers across. Now stop for a moment. Sit with that. Because here's where it gets lovely. 340,000 kilometers. What is that really? What's a thing that size? Well, that, almost exactly, is the distance from the Earth to the Moon. The Moon, that pale thing you've looked up at 1,000 times, hanging there in the dark. The distance to it, there and gone, is about the size of our entire model galaxy. So picture it. Hold the Earth in one hand and the Moon in the other, that whole gulf of black space between them. That entire span, that's the Milky Way, shrunk down so the sun is a single grain of sand. The whole galaxy, every star you've ever seen, every star you'll never see, all packed into a disk the width of the gap between us and the Moon. Now that's still vast. Earth to Moon is a long, long way. It took the Apollo astronauts 3 days to cross it, but it's a vastness you can almost feel now, isn't it? It has edges, it has a shape your mind can hold. That's what the model is for. To turn a number into a thing you can hold in your hands. And I want to be honest with you here, because honesty is the whole spirit of this journey. You'll sometimes hear people say that if the sun were a grain of sand, the galaxy would be the size of a continent, as big as a country, sprawling for thousands of kilometers. And that sounds wonderful, but it isn't quite right, not at this scale. At grain of sand sun, the galaxy is Earth to Moon sized the way I just described. To make the galaxy continent-sized, you'd have to shrink the sun much, much further down to a single atom. And that's a different model entirely. We're not going to do that tonight. We're going to keep one model, one honest model, and hold it the whole way. The sun is a grain of sand. The galaxy is the gap to the Moon. That's our world for the night. Simple, true. We won't switch it on you. So, we have our galaxy, 340,000 kilometers wide, all our stars inside it, and somewhere in that disk, off to one side, far from the center, sits one particular grain of sand, our sun. And here is the question that turns this whole model from a clever trick into something that quietly takes your breath away. How far away is the next grain of sand? The nearest star to our Sun is called Proxima Centauri, a small, dim, cool red star far fainter than our own. In real distances, Proxima is about 4.24 light-years away, the closest neighbor we have, our nearest grain of sand. So let's shrink that distance too by the same factor and find out how far apart our two grains sit in the model. The answer is about 14 kilometers. Let me let that settle because it deserves a long, slow moment. 2 grains of sand, each half a millimeter across. And the space between them, 14 kilometers. Not 14 centimeters, not 14 meters, 14 kilometers. If you set 1 grain of sand down on a table in front of you, the nearest other grain and the next nearest star to the Sun would be a grain of sand sitting on a table 14 kilometers away. In another town, across a river, over hills, past fields and roads and houses, 14 kilometers of empty space, and then finally 1 more half-millimeter speck. And between them, nothing. Almost perfectly nothing. Not a wisp, not a crumb, not so much as a mote of dust at this scale. Just emptiness, 14 kilometers of it, between 2 grains of sand. That's our neighborhood. That's how the stars actually sit. Not crowded, not bunched together in glowing rivers like the pictures. Spread out so thin, so impossibly thin, that 2 of the closest stars in the entire galaxy are, proportionally, like 2 grains of sand in 2 different towns. I find that one of the most peaceful facts I know, because we're so used to feeling crowded. The world is loud and full and pressing in. But the galaxy, the real galaxy, the one you actually live in, is mostly, overwhelmingly, almost entirely empty, quiet, spacious beyond imagining. There is so much room out there, so much soft black nothing between every single point of light. When you look up at a sky full of stars and it seems packed, dense, glittering edge to edge, that's an illusion of distance. Up close, each one is alone, a grain of sand with kilometers of dark on every side. So that's our model. Grain of sand, 14 kilometers, nothing between. Hold it gently, we'll need it the whole way out. Now, before we begin the journey itself, before we set off from the center toward that fuzzy distant edge, I want to tell you something that I think changes how you'll feel about everything that follows, something most people never stop to consider. And it's this: we have never seen the Milky Way. I don't mean from the inside. From the inside, of course, we see it all the time. That pale river of light arcing across a truly dark sky, the band of soft glow that gave the galaxy its name, the Milky Way, the Milky Road of the old stories. That's the galaxy seen edge on from within, our view through the flat plane of the disk, looking the long way through all those grains of sand toward the crowded center. We've seen that for as long as there have been eyes to look up. But from the outside, from above? Looking down on the whole spiral, the way you'd look down on a plate, seeing the arms wind out from the bar, seeing the shape of the thing entire? We have never once seen that. Not ever. And here's the part that always stops me. We never will. Think about every image you've ever seen labeled as the Milky Way. That gorgeous spiral, glowing blue and gold, arms curling out from a bright core, the whole majestic pinwheel hanging in space. You've seen 100 of them, on posters, in documentaries, on the covers of books. And every single one of them is a kind of gentle lie, because no human, no spacecraft, no camera has ever traveled far enough above our galaxy to take that picture. We are inside it. We have always been inside it. We are a grain of sand deep within the disk, and we cannot get out to look back. So where do those pictures come from? 2 places. Some of them are other galaxies entirely. When you see a stunning spiral and someone calls it the Milky Way, you're often actually looking at Andromeda, our great neighbor 2.5 million light-years away, or another lovely spiral called NGC 68744, which happens to resemble what we think we look like. They're stand-ins, body doubles, a photograph of someone else's home dressed up as a photograph of ours. And the rest of those images are artists' reconstructions, careful, beautiful, painstaking guesses built up from everything we've measured from the inside, the motions of stars, the glow of gas, the patterns in the dust, assembled into a portrait of a thing none of us has ever laid eyes on. An informed imagining, a picture drawn from the inside of a house of what the house must look like from the sky. And we will never have the real one. To take that photograph, you'd have to fly a camera tens of thousands of light-years straight up out of the disk, far enough to see the whole spiral spread below you. At the fastest speeds we can even dream of, that journey would take longer than humanity has existed, longer by far. The galaxy will have changed its shape entirely before any camera could get far enough out to capture the shape it has now. So the most familiar thing in the universe, our own home, the place that made us, the place we have always lived, is the one place we can never step back and see. Isn't that strange? Or you can see your own house. You can walk across the street and look at it. You can see your own face in a mirror, but you cannot see the galaxy you live in, not the real thing. You can only see it from within, looking the long way through and trust the careful drawings for the rest. So when we travel tonight, when I describe the spiral arms and the central bar and the great bright heart, hold this gently in your mind, that every picture of it is, in some sense, a beautiful guess. We know our home better than we've ever seen it. We've measured it without ever stepping outside. I'll come back to how we know all this later in the journey. How we can possibly map a thing we've never seen from the outside. There's an answer, and it's a wonderful one, and it involves looking at nearly 2 billion stars one at a time. But that's for further along the road. For now, I just want you to carry the feeling of it, the soft humility of it. We are about to tour a place we have never seen whole. We're going to walk through our own house in the dark, knowing it by touch, by memory, by the careful measurements of those who came before. And that's a tender thing when you think about it. A little like remembering a childhood home you can never return to. You know exactly where every room is. You just can't stand outside and look at it anymore. So let's settle into that. No rush. There's nowhere we have to be. We have the whole galaxy ahead of us and the whole night to cross it. Now, where to begin a journey across something so large? And you have to start somewhere. And the natural place, and the place everything else turns around, is the center, the heart of it. So that's where we'll go first, in our minds. And then we'll work our way slowly outward, arm by arm, until we reach the place where the stars finally thin out into nothing. Center to edge, the natural shape of the trip. But before we dive into that center, and it is a remarkable, strange, silent place, I promise you, with something at its very middle that I can't wait to tell you about. I want to set the stage gently. I want to give you the lay of the land, because for most of human history, people had no idea what they were even looking at. They saw that pale band across the sky, the Milky Way, and they told stories about it. Spilled milk from a goddess, a river of souls, a road of bones. But they had no notion that they were looking edge-on through a vast flat disk of hundreds of billions of stars. They didn't know the shape of it. They didn't know we lived inside a spiral. They didn't know there was a center at all, let alone what sat there. And for a long time, even when we began to suspect the shape, we pictured it wrong. We pictured the galaxy as something settled and known and tidy. A clean, glowing pinwheel full of stars packed close together, with us somewhere comfortably inside it. A finished thing, mapped and understood. It felt almost complete, like we'd sorted out our address and could move on to other questions. And nearly every part of that comfortable picture turns out to be wrong, or at least far stranger than we thought. The galaxy isn't crowded. We've already seen that, 2 grains of sand 14 kilometers apart. It isn't fully mapped. We've measured under 2 stars in every 100. It isn't even mostly made of the stuff we can see. Most of it, as we'll find, is invisible. And our address, that comfortable spot we thought we understood, turns out to be humbler and odder than the textbooks long claimed. We don't sit in a grand spiral arm. We sit in a quiet little spur off to the side, slightly above the main plane of the disk, drifting through a bubble of hot gas that an ancient explosion blew open around us. A modest neighborhood in a flatter, emptier, darker, more mysterious galaxy than anyone first imagined. That's the journey. From a black hole no one had ever photographed until just a few years ago, out through a bar of old red stars, along arms that aren't really solid things at all, but more like traffic jams of light, past our own quiet doorstep, into a halo of ancient wanderers, some of them stolen from a galaxy we once ate, and finally out past the last clear stars, into the dark fringe where the Milky Way doesn't end so much as forget to keep going. We have a long way to travel, and we're going to take it slowly, the way you'd walk a familiar path in the dark, letting your eyes adjust, in no hurry to reach the end. There's no rush at all. The stars aren't going anywhere on any time scale that matters to a single quiet night. They'll wait for us. So get a little more comfortable, loosen your shoulders, let the pillow take the full weight of your head. If your eyes are still open, you can let them close now. You won't miss anything because I'll keep talking slowly, and the pictures will build themselves in the dark behind your eyelids the way they always do. The grain of sand. The 14 kilometers of nothing. The galaxy the size of the gap to the moon. The home we've never seen from outside. We're going to begin at the very center now, at the still point that everything else turns around. And there's something waiting there in the dark. Something 4 million times heavier than our sun, and yet small enough to fit inside the orbit of the closest planet, and so quiet, so patient, that for nearly all of human history, no one even knew it was there. We only managed to take its picture for the very first time a few short years ago, and to find it, we had to give up on ordinary light entirely and learn to see in colors our eyes were never built for, peering through great curtains of dust that hide the heart of the galaxy from view. So let's go there, slowly, inward toward the center, toward that silent, enormous thing. Let me take you to the middle of everything you have ever known. But before we step all the way in, let me make sure you know who's speaking to you tonight and where you've arrived. Welcome to the Sleepy Scholar. It's so good to have you here, in whatever corner of the world you happen to be lying in right now. And I'm genuinely curious about that. Where are you watching from tonight? A bedroom with the curtains drawn, a couch with one lamp still glowing, a train rocking gently through the dark. Leave it in a comment if you feel like it, before sleep takes you. Tell me your corner of the night and what time it is where you are. I love reading them. And if these slow journeys are the kind of thing you'd like more of, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. It's the whole reason the next night exists. So, thank you truly, if you choose to. And to those of you already here, already subscribed, already part of this, thank you for coming back. There's no pressure either way. Stay, drift, sleep. The galaxy will keep turning regardless. Now, before we sink down into the center, I want to give you the size of the thing properly. because a number on its own is a useless little thing to fall asleep to. If I tell you the galaxy is 100,000 light-years across, what does that give you? Nothing. It's too big to hold. It slides right off the mind. So let's shrink it down until it fits in your hand, and let's do it honestly, because that's the whole point of tonight. Take the sun. Our own star, the one that warms your skin in summer, the one you've squinted at your whole life. It's about 1 1/3 million kilometers across. You could line up 109 Earths along its face. It is, by any human measure, unfathomably enormous. Now, shrink it. Shrink it down and down until it's the size of a single grain of fine sand, the kind that sticks to your fingertip at the beach, 0.5 millimeter wide. One small grain. To do that, we've shrunk everything by a factor of roughly 2,500 trillion. A 2, followed by 15 zeros, near enough. That's the magic number, and we're going to hold it for the whole journey, so it stays honest. No cheating, no swapping the ruler halfway through. So, the sun is now a grain of sand on your fingertip. The question that matters, the question that almost no one answers truthfully, is this. How far away is the next grain? How far to the nearest other star? The nearest star to us is called Proxima Centauri, a small, dim, red thing 4¼ light-years away. Shrink that distance by our magic number, and the next grain of sand sits about 14 kilometers away from the first. Sit with that for a moment, in the dark. 2 grains of sand, 14 kilometers apart. You could put 1 grain in your bedroom right now, and the next nearest grain, the next nearest star, would be on the far side of a city. And between them, nothing. Not another grain, not a pebble, not a speck. Just 14 kilometers of empty, silent, undisturbed dark. That is what the space between the stars is actually like. Not the crowded, glittering field the pictures show you. Just 2 tiny grains, impossibly far apart, with a great deal of nothing in between. And here's the part that surprises almost everyone, because it goes against every image you've ever seen. At that same scale, sun as a grain of sand, how big is the whole galaxy? The entire 100,000 light-year wheel of it? About 340,000 kilometers across. That's it. That's roughly the distance from the Earth to the Moon. The whole Milky Way, every one of its 100 billion stars, the entire spiral you've seen splashed across 1,000 posters, at the scale where the sun is a single grain of sand, the whole thing would just about reach from here to the Moon. Not the size of a continent. Not the size of a planet. The size of the gap to the Moon, filled almost entirely with nothing, sprinkled here and there with grains of sand 14 kilometers apart from each other. I know the artwork wants you to picture something dense and bright and full, a glowing pinwheel-packed edge to edge with light. But that brightness is a trick of distance, the way a far-off city looks like a solid sheet of light when really it's just scattered windows with enormous darkness between them. Up close, inside it, the galaxy is mostly, overwhelmingly, almost perfectly empty. And there's something wonderfully calming in that, I think. All that room, all that quiet, the stars not crowding each other at all, but keeping their vast, patient distances, like lamps left on in houses miles apart across a sleeping countryside. Now, I told you we'd be honest tonight, and here's the strangest piece of honesty of all, the one that gives me a small shiver every time. We have never seen it, the Milky Way, our own home. We have never once seen it from the outside. Every photograph you have ever looked at and thought, that's our galaxy, every glowing spiral on a textbook cover, every desktop wallpaper, every documentary opening shot, is not a photograph of the Milky Way. It can't be, because no eye, no camera, no spacecraft, has ever traveled far enough out to turn around and look back at us, and none ever will. To get far enough out to take that family portrait, you'd have to cross tens of thousands of light years of that empty dark, and nothing we've ever built moves at any speed that makes that a journey within 100 lifetimes, or 1,000, or 100,000. So what are all those pictures then? They're one of two things. Either they're photographs of a completely different galaxy, usually Andromeda, our great neighbor, or a beautiful spiral with a name like NGC 6744 that happens to look the way we think we look, quietly standing in for us, a portrait of a stranger we've decided resembles the family, or their paintings. Careful, brilliant reconstructions built up by artists and astronomers from everything we've managed to measure from the inside, the way you might draw the outside of a house you've only ever stood within. Educated, painstaking guesses, beautiful guesses, but guesses. We live inside this thing. We have lived inside it for our entire existence as a species, and for billions of years before that, and we have never seen its face. We have only ever felt our way around its rooms in the dark, mapping the walls by touch, listening to the echoes, piecing together a picture of a home we can never step back from to admire. There is something almost tender about that. A whole civilization working for centuries just to sketch the outline of the house it was born in. So how do we know anything at all? How do we know it's a spiral, that it has a bar across its middle, that we sit out toward the edge in a quiet little arm? That's the wonder of it, and that's exactly the path we're going to walk tonight. We're going to feel our way through the dark, room by room, from the very center all the way out to the last faint star, and I'll show you how we learned the shape of a home we've never seen. For a long time, people imagined the galaxy as a fairly tidy, settled thing, a flat, bright disk, a spiral, neatly drawn, with the sun somewhere comfortably inside it, a finished picture, more or less. The way you might think of your own house, solid, mapped, known, nothing left to discover. A golden age of certainty where the only things missing were a few details to be tidied up later. But the galaxy, like so many things we think we understand, turns out to be stranger and emptier and far less finished than the tidy picture suggests. The edges blur, the arms move, the center hides, and most of it, as we'll see, isn't even the kind of stuff we can shine a light on at all. So let's begin where everything turns. The center. The still point. We're going to drift inward now, slowly, through those great curtains of dust, toward the silent, enormous thing that sits at the heart of it all. The thing we only learned to photograph a few short years ago by learning to see in light our eyes were never given. Inward. Toward the middle of everything. No rush, just let me carry you there. There is something almost surreal about this. The idea that every star you have ever seen with your own eyes, every constellation, every quiet smear of light crossing the summer sky, all of it points toward a center you cannot look at directly. Not because it's too far away, not because we lack the instruments, but because the galaxy itself drew a curtain between us and its own heart. Billions and billions of tons of dust spiraled and layered and stacked across 26,000 light-years, blocking the visible light as completely as if someone had simply painted over the window. For most of human history, we did not know what lay at the center. We suspected something. The nature of galaxies, the way they swirl and hold together, hinted at something massive anchoring the middle, but we could not see it. And there is something quietly humbling about that. The idea that our own home kept its most important secret from us for so long, hidden in plain sight, right at the heart of the place we live, and we only needed to learn a different way of looking. We learned to look in radio waves first, then in infrared light which slips through dust the way a whisper slides under a closed door, then in X-rays. And slowly, piece by piece, we began to understand what was there. What is there is Sagittarius A star. You will sometimes see it written as Esca Ace, and the asterisk is not a footnote. It is part of the name read aloud as star. Named for the constellation Sagittarius, where the galactic center sits as seen from Earth, and the asterisk marks it as the compact radio source right at the center of the larger complex. A pinpoint. A silence so dense it bends reality. Sagittarius A is a supermassive black hole, and the word supermassive does real work here. It is not a casual intensifier. It weighs approximately 4.15 million times the mass of our Sun, not 4 million suns laid end to end, not the mass spread across 4 million volumes of space. All of that mass, and the gravitational equivalent of 4 million stars like ours, collapsed and concentrated into a region smaller than your imagination has probably allowed for. Its event horizon, the boundary beyond which nothing returns, spans roughly 24 million kilometers across. That sounds enormous, and in the ordinary world it would be. 24 million kilometers is about 62 times the distance from the Earth to the Moon all the way across. If you put it on a map next to anything human-sized, it is incomprehensible. But here is the thing about Sagittarius A, team. It is actually comparatively small for what it contains. 24 million kilometers at the scale of our solar system is less than the diameter of Mercury's orbit around the Sun. The innermost planet, making its tight little circles close in to the Sun, traces a path roughly 82 to 86 million kilometers across at its widest. Sagittarius A's event horizon fits comfortably inside that. 4 million solar masses, all the gravity that holds the inner galaxy in its long, slow waltz, contained within a sphere smaller than the first planet's orbit. Let that sit for a moment. No rush. When you look up at Mercury, the tiny, rocky, fast-moving dot close to the Sun's edge at twilight, you are looking at a distance that brackets the most extreme concentration of mass we know of in this galaxy. Smaller than that. All contained. All silent. And silent is the right word, because one of the stranger things about Sagittarius A is how quiet it is. Other galaxies have supermassive black holes at their centers that are active in ways you would notice from the other side of the universe. Quasars, active galactic nuclei, jets of hot plasma shooting out for millions of light years, blazing brighter than entire galaxies' worth of stars. Those are supermassive black holes that are actively consuming, swallowing enormous quantities of gas and dust, heating that infalling material to millions of degrees, generating light and radiation that can outshine everything else in the visible universe. Sagittarius A is not doing that. It is, by the standards of galactic centers, extraordinarily calm. It accretes very little matter today. There are occasional small flares, brief brightening events when a clump of gas wanders too close, or when it tears apart a small cloud. But nothing like the enormous luminosity of a truly active galactic nucleus. It sits there, patient, waiting. 4 million solar masses of stillness at the heart of a galaxy 250 billion years old in collective stellar history. And it is, for now, essentially switched off. This was one of the surprises when we finally managed to image it. That image came on the 12th of May 2022. Mark that date if you like. It is the kind of date that deserves to be remembered. Because on that day, the Event Horizon Telescope collaboration, a worldwide network of radio telescopes linked together to form an Earth-sized virtual dish, released the first direct image of Sagittarius A, a fuzzy orange ring of light, a bright donut of hot gas, glowing against the dark of the accretion region with a shadow at the center. The black hole's shadow, where the light bends and curves and cannot escape. It looks at first glance like something between a ring of fire and a smudged thumbprint, but what it actually is something no human eye had ever seen before that morning. Direct visual confirmation, however blurred, of the object at the center of our own galaxy. The thing that holds the Milky Way together, photographed for the first time 2 years and 26,000 years at the same moment. 2 years because that is roughly how long the collaboration spent processing the data, calibrating the instruments, accounting for the fact that SGRA is frustratingly difficult to image. It is much smaller and faster changing than the black hole at the center of M87, which they imaged first in 2019. Sagittarius A shifts and shimmers on timescales of minutes, which meant the team had to average across many observations and use sophisticated models to reconstruct a stable image. It was like trying to photograph a spinning, jittering coin in a blizzard. And 26,000 years, because that is how long the light, the radio waves really, in this case, spent crossing the galaxy before arriving at our telescopes. The event we imaged did not happen 2 years ago, it happened 26,000 years ago. We will come back to that. The light travel time deserves its own moment. But first, how do we know what Sagittarius A weighs? The number 4.15 million solar masses is not a guess. It is a measurement, and the measurement was made the same way you would weigh any massive object that you cannot touch. You watch something orbit it and you use the math. There is a star called S2. It is one of a small group of stars, either the S stars they are called, that orbit Sagittarius A, stummed in tight, fast, elliptical paths closer to the black hole than any star should reasonably be, swinging around it in the way that on a much smaller scale, a ball on a string swings around the hand holding it. S2 is the one we have tracked most carefully, and its orbit is extraordinary. S2 completes one full orbit around Sagittarius A in approximately 16 years. 16 years. Our solar system takes 225 million years to circle the galaxy once, and here is this star completing a full orbit in 16. The comparison is staggering even to try to hold in the mind, and these are not comparable scales, they are almost laughably different. But the number that stays with you is not the orbital period, it is the speed. At the closest point in its orbit, the point astronomers call periapsis, S2 is moving at approximately 7,650 kilometers per second. 7,650 kilometers every second. To give you a sense of what that means, the speed of light is roughly 300,000 kilometers per second. S2 at its fastest is traveling at about 2.5% the speed of light. That is fast enough that the effects of general relativity become measurable, not a theoretical prediction, but an observable fact. The light from S2 is measurably shifted and distorted by the black hole's gravity as the star swings past, a phenomenon called gravitational redshift, first predicted by Einstein's general theory of relativity in 1915 and confirmed, watching this one star scream around this one black hole, by the gravity collaboration. The gravity collaboration. You may want to hold that name. They are one of the central players in our understanding of Sagittarius A. A consortium of European and international astronomers and institutions using an instrument called gravity installed at the Very Large Telescope Interferometer in Chile, they have spent years monitoring the motion of S2 and other stars near the galactic center with extraordinary precision. And in 2019, they used those observations to produce the most precise measurement we have of both the mass of Sagittarius A, 4.15 million solar masses, and of our distance from the galactic center. That distance, 26,673 light-years, give or take roughly 100 light-years, approximately 8.178 kiloparsecs in the units astronomers prefer. This is the number, 8,178 kiloparsecs, that refined a value the International Astronomical Union had long held at approximately 8 kiloparsecs, a figure used for decades as the standard distance. The gravity result tightened it beautifully, and it matters because the galactic center distance is a fundamental anchor for almost everything else we measure about the Milky Way. Reinhard Genzel and Andrea Genzel at the Max Planck Institute for Extraterrestrial Physics, Gez at UCLA, spent decades leading the two independent teams that tracked the S-stars and established the black hole's existence through those orbital measurements. In 2020, they shared the Nobel Prize in Physics for that work, a Nobel Prize for watching a star go around something we cannot see, using light that left those stars 16 years before it told us anything. This is how science builds a picture out of darkness. So, we have a mass, we have a distance, we have an image. And you might be wondering, quite reasonably, if there is a 4 million solar mass black hole at the center of the galaxy, why are we not in danger? Why has it not swallowed us or the entire galaxy long ago? The answer is simple and oddly comforting: distance and stability. Gravity is extraordinary, but it does not reach out like a hand and grab. The galaxy is a gravitational system in balance, everything orbiting everything, each object on a path determined by the combined pull of all the mass around it. And that balance is remarkably stable over enormous timescales. The Sun, at 26,000 light-years from the center, is simply too far away for Sagittarius A's gravity to have any meaningful effect on its path beyond being part of the galactic background that keeps us in orbit at all. Think of it this way: the Sun orbits the galactic center at roughly 230 kilometers per second, a genuinely extraordinary speed that we never feel because everything around us is moving in roughly the same way. From our perspective, we are still. But in relation to the galaxy, we are flying, and that orbit is stable. The Sun has been completing these slow circles, one every 225 to 250 million years, for 4.5 billion years, and it will continue for billions more. Sagittarius A is not a drain. It is an anchor, a gravitational center around which the galaxy has organized itself over billions of years of evolution. A black hole does not suck in the cartoonish way. It gravitates. If you replaced the Sun with a black hole of identical mass, which would be a very small black hole, far smaller than a grain of sand, the Earth's orbit would not change by a single kilometer. It would be dark and cold and the end of everything we know, yes, but it would not be a gravitational catastrophe. The black hole's gravity would be exactly the same as the Sun's at the same distance.
Mass governs the gravity, not the compactness. Sagittarius A is only dangerous if you get very close, and very close means within the solar system scale at the very most, and we are 26,000 light-years away, safe, stable, quietly orbiting something we only photographed 3 years ago, at a distance that light takes 26,000 years to cross.
Which means, this is one of those facts that rewards sitting with for a moment before moving on, the light that arrived at the Event Horizon Telescope's arrays on the nights they were observing, the radio waves that eventually became that orange fuzzy ring in the 2022 image, left Sagittarius A approximately 26,000 years ago. The signals we detected in 2022 were generated in roughly the year 24,000 BCE. In the year 24,000 BCE, humans were alive. They were painting animals on cave walls in what would become France and Spain. The last ice age was still ongoing. The great ice sheets had not yet retreated from northern Europe and North America. The civilization of ancient Mesopotamia was still more than 15,000 years in the future. No writing, no cities, no domesticated wheat, just people, scattered across the land, surviving, telling stories around fires, looking up at the same smear of light we look at now, with no idea at all what was at its center. And 26,000 years before they looked up, Sagittarius A produced whatever variation it was producing, and the radio waves began their long journey outward through the dust, through the arms, through the local bubble, across the last 26,000 light-years of empty space, and arrived in the very large telescope arrays in Chile and in the radio telescopes scattered across the Earth that together form the Event Horizon Telescope and became, eventually, a picture. That is what it means for light to have a travel time. The image is not of now, it is a letter from deep time. And here is the strange part. We are always reading old letters. Every photon from the galactic center carries that same lag. When you look toward Sagittarius, toward the heart of the galaxy on a clear night, a faint brightening in the south of the Milky Way's band, you are not seeing the present. You are seeing 26,000 years ago. The center you are looking toward has evolved, changed, perhaps flared, perhaps dimmed, in ways we will not know about for another 26,000 years. We are reading news from a civilization that no longer exists, from a moment that has long since moved on. This is the thing about being inside a very large galaxy and being bound by the speed of light. You are always, at some level, out of date. Now, before we can drift outward from the center, we need to linger here a little longer, because right around Sagittarius A, in the very innermost region of the galaxy, there is something else worth slowing down to notice. The nuclear star cluster. This is the densest known stellar environment in our galaxy, and possibly one of the densest in the local universe, packed into a sphere just a few light-years across. Remember, the nearest star to the Sun is 4.24 light-years away, and that gap feels oceanic at our scale. There are millions of stars, not millions spread across thousands of light-years, millions concentrated into a region not much bigger than the gap between us and Proxima Centauri. The stellar density there is approximately 10 million times greater than the local solar neighborhood. 10 million times. Out here, where we live, a typical cubic light-year contains, on average, something like 0 stars. The stars are so spread out that most of the volume of our neighborhood is simply empty. Carry a cubic light-year all the way to the nuclear star cluster and fill it to that density, and you have not an empty box, but something almost beyond comprehension. Millions of stars in a volume your mind might have expected to hold one or none. What would it look like to live on a planet there? If you imagine standing on a rocky world in the nuclear star cluster, and it is pure imagination, because the conditions there are not hospitable in any way we understand, and you look up at night, you would not see the familiar scattered points of light we think of as stars. You would see a sky blazing with thousands of stars, each brighter than the full moon. Not a few bright points among the dark. The sky would be lit. There would be no real night in the sense we mean. The darkness between the stars and the majority of the sky, as we experience it from Earth, would be replaced with something more like a continuous soft fire. Every star in the nuclear star cluster close enough to be brilliant, the whole dome of the sky populated not with points, but with the kind of brightness we associate with the full moon, multiplied across thousands of sources simultaneously. It is genuinely hard to hold in the mind. Our experience of the night sky is shaped almost entirely by emptiness, by the fact that the nearest star is 4 light-years away, and the next nearest handful are 5, 6, 7, 8 light-years away. And the stars thin out rapidly from there, so most of what we see overhead is vacancy. We look up at the dark and notice the pinpricks against it. In the nuclear star cluster, that vacancy does not exist. The stars there also orbit Sagittarius A in ways that are visibly dramatic on human timescales. S2's 16-year orbit is the most extreme example we have tracked so far, but it is not alone. There is a whole zoo of stars close to the black hole, each on its own exotic path, some of them moving fast enough that over decades of careful observation, the curvature of their paths becomes detectable. This is what Genzel and Gez were watching, year after year, building up the data that earned them the Nobel Prize. Stars moving against the background of stars, describing ellipses, confirming by simple orbital mechanics that something of enormous mass sits at the focus of every one of those paths. We see the center in infrared because dust stops visible light cold. The galactic plane, the disk we live in, is not empty air. It is threaded throughout with clouds of gas and dust, not dust like the fine particles floating in sunlight through your window, but vast molecular clouds, some of them tens of light years across, cold and dark and opaque. In between us and the galactic center, stacked over 26,000 light years, those clouds block visible light almost entirely. If you point an ordinary optical telescope at the galactic center, you see nothing but foreground stars and dust and dark. The center is simply not visible. But infrared light, longer wavelengths, lower energy, able to slip through dust like a ghost through a wall, passes through. Radio waves pass through even more easily, and X-rays, which are generated by the extremely hot gas near the black hole, leak through in their own way. So we built instruments that could see in those wavelengths, and we pointed them at Sagittarius, and slowly the center resolved, the black hole, the nuclear star cluster, the dense clouds of gas, the ancient stars of the innermost bulge. This is also why, for most of human history, the center was a mystery we could not even properly frame. We could see that the galaxy had a center. The star density increased toward Sagittarius, the Milky Way's band brightened in that direction. But the heart of it was hidden. No classical astronomer could look through the dust and say, there is a 4 million solar mass black hole sitting there, quiet, surrounded by a cluster of millions of stars, orbiting in a sphere a few light years across. That knowledge is, in the sweep of astronomy's history, extraordinarily recent, and it is built on the ability to look in light that human eyes were never designed to see. Radio waves, discovered as electromagnetic radiation by Heinrich Hertz in 1887. Infrared, identified by William Herschel in 1800. X-rays, discovered by Wilhelm Röntgen in 1895. The tools that revealed the galactic center were themselves less than 200 years old, and the galactic center would have remained permanently hidden without them. We are, as a species, very new to this kind of seeing. We learn to see the center of our own galaxy within the lifetimes of people still alive today. There is something almost moving about that if you let it be. The galaxy did not change. The black hole did not emerge recently. The nuclear star cluster has been there, blazing in the dark, for billions of years. Only we changed. Only our instruments evolved. Only our mathematics deepened. Only our networks of telescopes spread across the Earth and up into orbit until we finally had eyes capable of looking through the dust. And what we found was not a threat, not an active destroyer of worlds, but a quiet, enormous, ancient thing surrounded by millions of stars, sitting still at the center of a galaxy it has helped shape over billions of years, photographed for the first time only 3 years ago, sending us signals that left before the last ice age. Let that be what it is: quiet, old, real. The dust lanes, those great curtains we mentioned, they are not incidental. They are some of the richest parts of the galaxy. Cold molecular clouds threaded through the disk and especially thick in the inner regions, are where new stars are born. The dust is not sterile obstruction, it is the nursery. The very thing that hid the galactic center from us for so long is the same kind of material out of which the center's stars, and ours, were made. The galaxy hides behind the stuff it uses to build itself. There is something almost poetic in that, if you are inclined to see it. We will not linger on the poetry for too long. There is a long journey ahead. Outward, through the bar, through the great spiral arms, all the way to the sun's quiet spur, and then beyond, into the halo and the dark. But it matters to have stood here first. Here at the center, here where the black hole sits in silence, 4 million solar masses of stillness, photographed for the first time in the year 2022. Here where star S2 swings past at 2.5% the speed of light, a natural speedometer for something we cannot see. Here where the nuclear star cluster blazes with 10 million times the stellar density of our own quiet neighborhood. Here where the light arriving at our telescopes tells us about a moment 26,000 years before we looked. This is the core, the still point, the thing around which everything else in this video is organized, the 250 billion years of combined starlight, the spiral arms, the halo, the dark matter, the last faint star at the fuzzy edge. All of it has this at its center. And now we drift outward. Not quickly. The galaxy is large. There is no hurry. Let the picture expand gradually, the way a room gets bigger as you back away from the wall. Between the galactic center and the spiral arms, there is a structure that took us a surprisingly long time to recognize in our own galaxy. We had seen it in other galaxies. We had catalogued it, classified it, built whole naming systems around it. But identifying it in the Milky Way from the inside, while sitting in the disk and looking out through layers of gas and dust, proved more difficult than almost any comparable problem in galactic astronomy. The bar. The Milky Way is what astronomers classify as a barred spiral galaxy. The designation is SBBC, a notation that means, in the taxonomy of galaxies, a barred spiral of intermediate openness, not too tightly wound, not too loosely, with a bar across the center. And that bar, a roughly cigar-shaped or elongated structure of mostly older, redder stars, stretches out from the nuclear region for somewhere between 10,000 and 14,000 light-years on either side of the center. It is tilted. If you could look at the galaxy from outside, and we cannot, and we will come back to exactly why that is, but for the moment indulge the imagining, you would see the bar crossing the center at an angle somewhere between 27 and 45 degrees off the line, pointing straight at us. Not pointing toward us like an arrow, angled, slightly diagonal. Large enough that its two ends anchor the major spiral arms that sweep out from them. Why are there bars? The honest answer is that astronomers are still working out the full dynamics, but the general picture involves the orbits of stars in the inner galaxy. In a barred galaxy, large fractions of the inner stars are on elongated orbits. Orbits that are stretched rather than circular, lined up roughly along the bar's major axis. And this alignment of many elongated orbits creates the bar-like overdensity we observe. It is a self-reinforcing structure, stable over timescales of billions of years, sculpted out of nothing but gravity and the initial conditions of how the galaxy formed. For us, inside the galaxy, the bar was effectively invisible for most of the history of astronomy. The dust blocked the view. The visible light from stars in the bar region could not reach us clearly. And even in the directions where some light did come through, it was hard to disentangle the bar from the general complexity of the inner disk. What changed was infrared. When the COBE satellite, the Cosmic Background Explorer, launched in 1989, mapped the infrared sky, it revealed a lopsided asymmetry in the brightness of the inner galaxy that was exactly what you would expect from a bar tilted at an angle to our line of sight. One end of the bar was closer to us, and therefore appeared brighter and covered a larger apparent area of sky. The other end was farther, dimmer, smaller. This lopsidedness in the COBE maps was one of the first strong lines of evidence that the Milky Way's bar was real. Then came 2MASS, the 2-micron all-sky survey, which built a more detailed infrared map. Then OGLE, the optical gravitational lensing experiment, which tracked red clump giant stars, evolved stars whose intrinsic brightness is well understood and which therefore serve as reliable distance markers through the central regions. And then the VVV survey, the VISTA variables in the Via Lactea, which used infrared cameras on the European Southern Observatory's VISTA telescope to map billions of stars in the inner galaxy with great precision. What those surveys revealed, piece by piece, was not just a bar, but a bar with a particular three-dimensional shape that was, in its way, a surprise. When you view the inner galaxy edge on and map out where the red clump giant stars are distributed, you find two overdensities, two thickenings, one above the midplane and one below, that trace a shape not like a simple cigar, but like a peanut, or like an X, if you look at it the right way, a boxy peanut, or an X-shaped bulge. The names are slightly ungainly, but they describe the same thing. The three-dimensional distribution of stars in the bar has a characteristic double peak structure, a bowing outward above and below the plane that creates the visual impression of an X when you plot it up. This was formalized by a 2013 study by Weg and Gerhard, using the VVV data to map the distribution of red clump stars in 3 dimensions with unprecedented care. And the X-shaped boxy peanut structure they found is now understood to be the natural result of a bar buckling under its own dynamics. A bar that formed, then became unstable in the vertical direction and buckled upward and downward in a way that redistributes its stars into exactly that peanut shape. It is a structure that exists in many barred galaxies. We had seen it in edge-on galaxies elsewhere, recognized the X in the brightness profiles of their central regions. We just did not know for certain that our own galaxy had it too, until the infrared surveys gave us enough data to map it. We live in a galaxy with an X-shaped heart. That is a reasonably strange thing to know, and we have known it with confidence for barely more than a decade. The bar is not a static thing either. It rotates. The whole structure, slowly, like a propeller, around the galactic center with a pattern speed that is different from the orbital speed of individual stars. Stars pass through the bar, get caught up in its elongated orbits, participate in its structure for a while, and then drift out again. It is more like a sustained wave or a persistent traffic pattern than a solid object. But it holds its shape over enormous timescales, shaped and sustained by the collective gravity of all those aligned orbits. And at its ends, something important happens. The ends of the bar are where the major spiral arms anchor, where the bar's outstretched tips interact with the material of the disk. Density waves begin. The arms curl outward from there, winding their way through the galaxy's disk. And this is where we are headed next. But before we follow the arms outward, there is one more thing worth knowing about the central bar region, something that the surveys revealed almost incidentally. The stars in the bar are old, predominantly old, redder, cooler, more evolved than the hot blue-white stars of the spiral arms. The inner galaxy is largely a city of ancient stars, formed early in the galaxy's history, billions of years ago, when the initial collapse of gas and dust produced an enormous burst of star formation. The bar is, in some sense, a fossil, a record of the early universe preserved in the orbits of old stars, held together by gravity into a shape that has persisted through billions of years of galactic evolution. The outer disk, the arms, those are different. Younger, actively forming stars, but here at the center the bar is old, and the black hole at its heart is older still. So we have the center, we have the black hole, 4 million solar masses, photographed for the first time in 2022. We have the star S2 orbiting every 16 years at 2.5% the speed of light. We have the nuclear star cluster, blazing with 10 million times the stellar density of our neighborhood. We have the light that left 26,000 years ago, still arriving, still telling us about a moment before the Ice Age ended. We have the dust lanes that hid all of this from us for most of human history, and the infrared and radio light that finally let us see through them. We have the bar, X-shaped, peanut-bulged, anchoring the arms, rotating slowly, built of ancient stars. This is the heart of the galaxy. The quiet, dense, complex, obstinately hidden core. And now the arms reach outward from here. Two great spiraling structures of gas and newborn stars, tracing their slow curves across tens of thousands of light years. That is where we are going next. Out of the dust, into the arms. Slowly, there is no rush. The spiral has been there for billions of years, and it will be there long after this particular night is over. You do not have to hurry to find it. It has been waiting for you all along, 26,000 light-years in one direction, written in dust and starlight and the orbits of 100 billion suns. Just let me carry you there. So let us begin with the arms themselves and how they work. Because there is something that almost every picture of the Milky Way gets quietly wrong. A small deception built into every glowing spiral illustration, every textbook diagram, every poster that shows our galaxy as a luminous pinwheel of stars. The arms in those pictures look like rivers, fixed, permanent rivers of stars that have always been there and will always remain, stars flowing through them like water through channels, the arms themselves as real and solid as the banks that hold them. But that is not what they are, not at all. To understand what a spiral arm actually is, it helps to think about something much smaller and much closer to home. Think about a motorway, a long, busy motorway on a weekday afternoon. The traffic is flowing, but somewhere ahead there is a slow section. A lane narrowing, perhaps. Roadworks, and what you see from a distance is a cluster of cars, tightly packed, moving slowly. A visible knot in the stream, and then on the far side of the slow section, the cars accelerate and thin out again, spreading back to normal spacing. Now here is the thing, that knot of cars is not the same cars from 1 minute to the next. Cars arrive at the back of it, slow down, pack in. Then they reach the front, speed up, and leave. Individual cars are constantly passing through the jam, but the jam itself stays roughly in place, moving perhaps slowly forward or even backward relative to the general traffic flow, because it is a pattern in the density of the cars, not a fixed group of cars. The cars are transient, the pattern persists. That is what a spiral arm is. It is a density wave, a region where gas and stars pile up slightly like traffic slowing at a bottleneck before continuing on their way. The stars and gas clouds that make up the galaxy are all orbiting the galactic center, and as they do, they pass through these slow regions, these density waves. They bunch together, slow briefly in the cosmic sense, then continue outward and onward. This idea has a name. It is called the Lin-Shu density wave theory, proposed by the astrophysicists Chia-Chiao Lin and Frank Shu in 1964. Lin and Shu were looking for an explanation for a persistent puzzle. Why do spiral galaxies have arms at all, when the differential rotation of a galaxy, the fact that the inner parts orbit faster than the outer parts, should wind any fixed structure into a tight, featureless smear within a few billion years? If the arms were fixed groups of stars, they would have wound themselves into an unrecognizable blur long ago. They have not, so they cannot be fixed. They must be something else. The density wave was the answer. A wave is not a thing. It is a pattern moving through things. And like a wave on water, as the water molecules themselves just bob up and down, but the wave travels. The density wave moves through the galaxy's stars and gas, leaving the stars themselves behind to continue their orbits, while the pattern persists. The arms rotate, but not at the same speed as the stars. The wave pattern has its own angular velocity, typically slower than the orbital speed of the stars in the inner disk. Stars catch up to the wave, pass through it, emerge from the other side. In the outer disk, the situation can reverse and stars overtake the wave more slowly. The arms are, in a very real sense, places where the galaxy is momentarily thinking about itself, a slow-moving ripple of compression traveling through a sea of orbiting suns. Now here is the crucial part. Here is why the arms look so bright and so vivid in those pictures. When gas and dust pass through the density wave, when they slow and compress in the arm region, the pressure squeezes them. And when gas is squeezed sufficiently, it can collapse. And when it collapses with enough mass, it ignites. A star is born. The arms, then, are nurseries. The compression of the density wave triggers star formation on a grand scale, and the stars that form there are, at first, numerous and brilliant and hot. Massive stars, stars many times heavier than the Sun, glow blue-white, ferociously bright, burning through their fuel at a staggering rate. And because they burn so fast, they also die fast. A very massive star might live only a few million years before detonating as a supernova. Compare that to the Sun, which has already been alive for 4.5 billion years and has perhaps 5 billion more to go. These hot, blue-white, short-lived stars never have time to drift far from where they were born. They live and die inside the arm, and they are so much brighter than older stars that they dominate the light we see from the arm region. The arm glows not because more stars live there permanently, but because the stars that are born there are so intensely luminous that they illuminate the whole region, and then they are gone. Think of it this way: if you lit 1,000 birthday candles in a room and also placed one enormous searchlight in the corner, you would mostly see the searchlight. The arms glow with searchlights, brilliant, furious, short-lived, and those searchlights are constantly being replaced by the ongoing compression of the density wave, while older, dimmer stars have long since drifted out and away, too faint to notice. Between the arms, in the inter-arm regions where the gas has had time to thin out and where no compression drives new star formation, the older, redder, quieter stars still orbit. But they are faint. They do not announce themselves. The galaxy, viewed from outside, would look relatively dark between the arms, not because stars are absent, but because the brilliant young blue ones are not there. So the spiral arms are a kind of ongoing creative explosion. A wave of compression moves slowly around the galaxy, and everything it touches is turned briefly, brilliantly, into new suns. Now the Milky Way's arms have names, and it is worth spending a moment with them because this is, after all, a journey. We are trying to find our place in this. There are two dominant major arms anchored at the ends of the central bar, reaching out and curving around in the grand spiral. One is called the Scutum-Centaurus arm. It sweeps out from one end of the bar in a long, graceful arc, curving through the inner galaxy. The other, on the opposite side, is the Perseus arm, the great outer arm, curving through the far reaches of the disk. These two are the structural pillars, the main spirals from which the galaxy gets its pinwheel shape. If you were somehow above the Milky Way, looking down at the whole disk, Scutum-Centaurus and Perseus would be the two dominant features you noticed, winding out from the bar in a pattern like the shape of a nautilus shell or a curling wave seen from above. But there are other arms, or arm-like structures, winding between and beyond them. The Norma arm. The Sagittarius arm, closer to the center than the Perseus arm, one of the features that when you look toward the galactic core on a dark summer night gives the Milky Way that faint band of extra light, and the outer arm curling far out toward the edge of the disk, faint and distant. There has been genuine debate among astronomers about how many arms the Milky Way really has, and how significant each one is. The Spitzer Space Telescope's survey of the inner galaxy, a project called GLIMPSE that reported its findings in 2008, made a case for the Milky Way being primarily a two-armed spiral in terms of stellar structure, with the other features being gas-rich minor structures rather than true major stellar arms. The picture has continued to be revised as better data arrives. The galaxy, as it so often does, resists tidy categorization, but there is one more arm, one that matters to us personally, one that is our home. Its name is the Orion Arm, or, depending on which source you read, the Orion Cygnus Arm, or the Local Arm, or the Orion Spur. It is the one feature of the galaxy's spiral structure that is not a matter of abstract astronomy for us. It is the address on the envelope. We live here, and for a long time, the conventional picture of the Orion Arm was not flattering. It was typically described as a minor spur, a small, somewhat unremarkable bridge of gas and stars between the two major arms on either side, the Sagittarius Arm inward and the Perseus Arm outward. A backwater, essentially. Not even a proper arm, just a thickening, a stub, a piece of the spiral that did not quite make it to full arm status. There is something quietly amusing about that. Out of all the positions available in an entire galaxy, we ended up in the minor spur, not even a main thoroughfare, a side road between two larger ones. But the picture has changed. In 2016, a team of astronomers using a technique called Very Long Baseline Interferometry, VLBI, a method of measuring the parallax of distant objects with extraordinary precision by linking radio telescopes spread across the Earth, published new measurements of star-forming regions in the Orion Arm. This was the BeSSeL Survey, the Bar and Spiral Structure Legacy Survey, and the work of Xu and colleagues in 2016, published in Science Advances, painted a different picture than the old textbook spur. The local arm, they found, is not a stub. It is longer than previously mapped, it has its own branches, its own significant star-forming regions, a density and extent that begins to rival the major arms in at least some respects. It is still not classified as one of the two main stellar arms anchored to the bar, but calling it merely a minor spur, the 2016 data suggested, was selling it short. It is a substantial structure in its own right. Our street, it turns out, may be a real street after all, not just a shortcut between more important ones. This matters for more than civic pride. It matters because our understanding of our own position in the galaxy has always been limited by the fact that we are inside it. Mapping the spiral structure of the Milky Way from within is a bit like trying to understand the floor plan of a house while standing in one of the rooms with the lights off. You can feel walls, guess at doorways, infer the general shape from the sounds around you, but you cannot simply look down and see the whole thing spread out before you. For most of human history, we did not even know we were in a galaxy. The stars appeared as a fixed sphere of lights, and the soft glow of the Milky Way on a dark night was simply a feature of the sky. Beautiful, mysterious, unexplained. It was not until the early 20th century that the true nature of the Milky Way began to emerge, and not until the second half of the 20th century, with the arrival of radio telescopes capable of peering through the dust that blocks optical light, that the spiral structure became clear at all. We are still mapping it, still adding detail, still revising. The Orion Arm's promotion from spur to something more substantial is a recent correction. There will be more. We are, in a very real sense, still finding our way home. So here we are then, in the Orion Arm, 26,000 light-years from the center, orbiting in the outer middle regions of the galactic disk, not at the heart of anything, not at the edge. Somewhere between, in a stretch of the galaxy that is neither the blazing density of the inner disk nor the thin, dark outer reaches. A quiet neighborhood as galactic neighborhoods go. But quiet does not mean featureless. Because where we sit right now in this moment is inside something remarkable. It is called the local bubble. Imagine a soap bubble blown inside a thick foam, a spherical or irregular cavity, the interior of which is cleared out relative to the surrounding medium. The foam all around it is dense and complex, full of gas and dust clouds and star-forming material. But inside the bubble, the gas is thinner, hotter, more diffuse, evacuated essentially into a region of relative emptiness compared to the interstellar medium outside. The local bubble is a cavity in the interstellar gas and dust that surrounds the Sun, roughly 1,000 light-years across in most directions. Not a perfect sphere, more like an irregular, lumpy volume of cleared-out space. And the reason it exists, the reason this pocket of thinned-out, hot gas surrounds us, is that something exploded here. Several somethings, in fact. Over the last several tens of millions of years, a series of supernovae detonated in this region of the galaxy, one after another. Stars that lived fast and died violently, sending shockwaves through the surrounding gas, sweeping it outward, carving out this bubble of thinned, heated interstellar medium. The best current estimates suggest the bubble began forming roughly 14 million years ago, shaped by something like 15 to 20 supernovae, occurring in what was likely a loose association of massive stars passing through this part of the arm. In 2022, a team led by Catherine Zucker, whose work was published in Nature, produced a remarkable three-dimensional map of the local bubble's surface. What they found, tracing it using the extraordinary positional data from the ESA Gaia mission, was that nearly all of the nearby star-forming regions, the molecular clouds within a few thousand light-years of the Sun, the nurseries of new stars in our galactic neighborhood, are arranged on the surface of the bubble, sitting on its skin like towns built at the edge of a cleared valley. The bubble expanded, swept material outward, and those piles of swept-up gas and dust became the birthplaces of new stars. We are, in a sense, the inheritors of those ancient explosions. The Sun itself was not born here. It arrived from elsewhere over its long galactic journey. But the space around us was shaped by supernovae that preceded us by millions of years, and those ancient detonations created the relatively clear, warm pocket of interstellar medium that the Sun and its planets now travel through. It is one of the quieter revelations of modern astronomy. You are, right now, drifting through the interior of a supernova remnant. The explosion that carved this space happened 14 million years ago, while early primates were just beginning to diversify on a warm African planet. And the bubble it left is still here, still roughly intact, still warm and thin and clear compared to the denser material beyond its walls. The galaxy, it turns out, is full of these structures. Stellar winds and supernovae carve out volumes of space, compress material into rings and shells, trigger new star formation at their edges. The interstellar medium is not smooth or uniform. It is a churning, multi-phase structure of hot bubbles and cold clouds and warm filaments, all interpenetrating, all constantly being disrupted and reformed. The local bubble is simply the one we happen to live inside. And outside the bubble's walls, a few hundred light-years away, the star-forming regions that Zucker and her colleagues mapped: Taurus, Ophiuchus, Perseus, Lupus, Chamaeleon. The nurseries of new suns sitting at the edge of the cavity that older explosions cleared. We can look out at them and know that stars are being born there, right now, in the compressed gas at the bubble's surface. Stars that will live and die long after the Earth is gone. The cycle continues, as it has for billions of years, but let us not forget movement, because everything in this picture, the Sun, the local bubble, the Orion Arm, all of it is moving. The galaxy is not static. It is not a fixed diagram pinned to a board. Every component of it is in constant, graceful, almost unimaginably slow motion, and the Sun is no exception. The Sun is moving through the galaxy at roughly 230 kilometers per second. That is its orbital speed, the speed at which it circles the galactic center, swept along in the great rotation of the disk. 230 kilometers per second is an extraordinary number by any everyday standard. At that speed, you could travel from one side of the Earth to the other in under a minute. You could cross the distance from the Earth to the Moon in about half an hour. And yet, at that speed, it still takes the Sun approximately 225 to 250 million years to complete one full orbit of the galaxy. One galactic year, one circuit around the center, 250 million years. Let that settle for a moment if you are still following this. The Sun is moving at 230 kilometers per second, and its lap around the center takes 250 million years. That number tells you more viscerally than almost any other statistic in this journey just how enormous the galaxy truly is, because it means the Sun has been alive for 4.5 billion years, and in all that time it has completed only about 18 to 20 orbits. 20 laps of the galaxy in 4.5 billion years. Think of your own life and all the times you have moved around a building or a city or a familiar route. The Earth orbits the Sun once a year. The Sun orbits the galaxy once every 250 million years. We have been tracking the Earth's orbit around the Sun for a few thousand years of recorded history, a fraction of one Earth year compared to one galactic year. Our entire written civilization is a rounding error in the cosmic calendar of the Milky Way's rotation. Now that last galactic year, the most recent time the Sun completed a circuit and returned approximately to this position in the sky, and that was 250 million years ago. In geological terms, that was roughly the time of the Permian-Triassic extinction event, the largest mass extinction in Earth's history, the one that wiped out perhaps 96% of marine species. The world looked completely different. The continents were assembled into the supercontinent Pangaea. The oceans had different coastlines, different temperatures, different chemistry. And go back one galactic year before that, 500 million years ago, and we are deep in the Cambrian, when complex animal life was only just beginning to diversify in the seas. One galactic year before that, 750 million years ago, even earlier, a world of simple life, bacteria, and single-celled organisms, a planet still largely innocent of animals of any kind. The Sun has been doing this for the entirety of complex life on Earth and deep into the time before it. 20 orbits, 20 long, slow circuits of the center, each one taking longer than the whole history of vertebrate animals. The galaxy is patient in a way that language was simply not built to hold. And while the Sun circles in this graceful horizontal orbit, it is also doing something else, something gentler, something that in the context of the vast galactic plane is a very small movement. But over millions of years, it adds up. The Sun bobs. Not dramatically, not in any way you would notice over a human lifetime or even over the span of human civilization, but the Sun is not locked in a flat, perfectly horizontal orbit in the plane of the galaxy's disk. It oscillates gently up and down through the midplane like a horse on a very slow and enormous carousel. It crosses the midplane, rises above it, reaches some maximum height, falls back, crosses the midplane again, dips below, reaches a maximum depth, and returns. One complete bob, up, over, down, back, takes somewhere between 60 and 70 million years. Right now, the Sun is above the midplane, about 60 to 70 light years above it in the estimates that current measurements support. Not far in the context of the disk, which is roughly 1,000 light years thick in the thin disk component. 60 or 70 light years above the midplane is like being a few millimeters above the center of a dinner plate, barely noticeable against the plate's width, but it is above. This bobbing has consequences. When the Sun passes through the denser regions of the galactic plane, the gravitational environment changes slightly. Some scientists have speculated that this oscillation might correlate, very loosely and controversially, with variations in the rate at which material from the outer solar system might be disturbed, comets perturbed, impacts changing in frequency. The evidence for a direct causal link is not strong, and this remains speculative territory. But the oscillation itself is well-established physics. The Sun moves through the disk the way a swimmer bobs through gentle swells, endlessly, as it has for billions of years. And in all of this, the orbiting, the bobbing, the passage through arms and bubbles and dust clouds, the Sun has never once seen the galaxy from outside. It has never risen above the disk far enough to look down at the whole structure. It never will. The disk is too thick, the Sun's excursions too small. The best view we will ever have of the Milky Way from something resembling outside is the view we have of other galaxies. Andromeda, say, 2.5 million light-years away, which we can see in its full tilted spiral glory because we are looking at it from out here, not from inside it. But our own galaxy will always be the view from within, the view through dust and gas and the crowded background of the disk itself. That is something to sit with for a moment before we move outward into the halo. We have been on this journey for some time now, from the black hole at the center, out through the star cluster and the dust lanes, through the bar with its X-shaped bulge, into the spiral arms with their density waves and brilliant blue-white nurseries, to this quiet spur between two major arms where the Sun has settled for the moment. We have located ourselves precisely, or as precisely as current data allows, 26,000 light-years from the center in the Orion Arm, about 60 light-years above the midplane, inside the local bubble, moving at 230 kilometers per second through a galaxy we have never seen from outside, on lap number 20 of an orbit that takes 250 million years. It is a strange address, strange in its precision, strange in its humility. We are neither at the center of things nor at the edge. We are somewhere between, in a region that is, by the standards of the galaxy's denser zones, relatively quiet, relatively empty, relatively, and this word is doing real work here, safe. Because the galactic center, with its nuclear star cluster and its dense stellar environment and its ancient radiation from supernovae past, is not where you want to be if you are a planet trying to sustain life for billions of years. The inner galaxy is a more violent neighborhood, more stellar interactions, more radiation, more disturbance. Out here in the disk's middle regions, the Sun can orbit in its gentle lap without being jostled too dramatically. The Orion Arm is, in a quiet way, a fortunate address. Not destined, not designed, just the result of where the Sun happened to form 4.5 billion years ago from a cloud of gas and dust in this part of the disk. But fortunate in retrospect, and worth acknowledging. So we are here, in this spur, in this bubble, moving at this speed, on this orbit. the galaxy curving away from us in every direction, most of it hidden, most of it darkness, most of it the spaces between stars that are so much wider than the stars themselves. And if you think back to the grain of sand, if you carry that model with you as we continue outward, the picture becomes clearer in its strangeness. In that model, where the Sun is a grain of fine sand 0.5 millimeter across, the nearest star to us, Proxima Centauri at 4¼ light-years, is another grain of sand somewhere around 14 kilometers away. The Orion Arm in this model is a loose scattering of grains spread across hundreds of thousands of kilometers. The distance to the galactic center, 26,000 light-years, works out to a distance of roughly 90 million kilometers in the model, about the distance from the Earth to the Sun in real life. So in the grain of sand galaxy, you would need to travel a distance equivalent to the Sun-Earth gap just to reach the center of the Milky Way. And the galaxy's full width, 100,000 light-years of disk, would span roughly 340,000 kilometers, close to the distance from the Earth to the Moon. And between those grains of sand in all that space, essentially nothing. The galaxy is not a crowded place. It is not the dense, luminous, star-packed pinwheel of the posters. It is mostly dark, mostly nothing. A vast, thin, almost empty disk turning slowly in the dark with a few 100 billion tiny lights scattered through it at distances that, by the standards of the lights themselves, are almost incomprehensible. The arms glow because the lights that happen to be brightest are concentrated there for reasons of physics and timing, not because space is tight. The center blazes because the density is genuinely higher there, thousands of stars per cubic light-year instead of roughly 1 per 2 or 300 cubic light-years out here. But even at the center, even in the nuclear star cluster with its 10 million times higher stellar density than our neighborhood, there is still enormous space between each star. The scales involved mean that even the densest stellar environments in the galaxy are, by the standards of the objects within them, mostly nothing at all. This is one of the great counterintuitive truths of astrophysics. All that light, all those hundreds of billions of suns, and the galaxy is still overwhelmingly, almost achingly, empty. But there is another kind of emptiness we have not fully spoken to yet, and it is more profound still, because the visible matter, the stars, the gas, the dust, all of it is not actually most of what the galaxy is made of, not even close. The stars we see are the glints. They are the foam on the surface of something far deeper. And to understand the true scale of the Milky Way, we need to go up and out, away from the disk into the halo, and then further still into the vast invisible structure that surrounds everything we have described so far. But that is a different layer of the galaxy, and it deserves its own unhurried space. We are not quite there yet. First, let us pause here in the Orion Arm, 60 light-years above the midplane, inside our ancient supernova bubble on lap 20 of a 250 million-year orbit, and let the scale of the bar and the arms settle. The bar is roughly 10,000 to 14,000 light-years long. It sits at the center of the disk, tilted by 27 to 45 degrees relative to our line of sight toward the galactic center. It is built of old, red, metal-poor stars. Stars that formed early in the galaxy's history, when the gas was less enriched with the heavier elements that later generations of supernova explosions would seed into the interstellar medium. These old stars have been orbiting for billions of years, and over time their orbits have aligned and reinforced into the elongated bar structure, a self-sustaining feature of the galaxy's gravitational dynamics. We did not know the bar was there, really know it, mapped it, seen its true shape, until infrared light gave us the means to see through the dust. The COBE satellite in the 1990s was one of the first instruments to trace it clearly, its infrared detectors mapping the warm glow of the old stars in the central region and finding the elongated bar-shaped overdensity. Later, the 2-micron all-sky survey, 2MASS, added finer detail. The optical gravitational lensing experiment, OGLE, and the vista variables in the Via Láctea survey, VVV, continued the work, building up a detailed 3-dimensional picture of the central structure. And the work of Christopher Wegg and Ortwin Gerhard in 2013, using red clump giant stars as standard candles to map the bar's 3-dimensional shape, confirmed the X-shaped or boxy peanut bulge, that strange 3-dimensional boxing glove shape that the bar makes when viewed edge-on, a result of stars in the bar following resonant orbits that stack up into that distinctive form. Every one of those discoveries required us to work around the fundamental obstacle, the dust. The galactic center and the bar are hidden from optical eyes behind roughly 30 magnitudes of visual extinction, meaning that the light from those regions, if we could only see in visible wavelengths, is dimmed by a factor of 1 trillion. Completely invisible to naked eye stargazers and to ordinary telescopes, the night sky over the galactic center is, in optical light, essentially opaque. Centuries of astronomers looked towards Sagittarius and saw only stars of the nearby disk, with no hint of what lay beyond the curtain. Infrared and radio and X-ray astronomy tore the curtain aside. And behind it was all of this: the bar, the black hole, the star cluster, the ancient population of old red stars stretching into the bulge, an entire hidden heart of the galaxy, invisible to human eyes for all but the last few decades of our civilization. It is worth pausing on that. We have been here, on this planet, for hundreds of thousands of years. We have watched the night sky for all of recorded history. And the center of our own galaxy, the physical center of the place we live, was invisible to us until the latter half of the 20th century, hidden not by distance but by dust, by particles of carbon and silicate smaller than a human hair, scattered so thickly through the interstellar medium that they blocked every photon of visible light from the center before it could reach us. We have known the shape of our galaxy's arms for a matter of decades. We have known the bar's true form for a little over 30 years. We confirmed the existence of the black hole at the center well enough to name it as a near certainty in the 1990s and photographed it for the first time in 2022. The knowledge is young, the tools are recent, the picture is still being drawn. And the arms themselves, the Scutum-Centaurus sweeping out from one end of the bar, the Perseus reaching out from the other, the Sagittarius and Norma and outer arms, and the Orion spur winding between, are all things we have mapped from inside, from within the disk, using the positions and motions of stars and gas clouds, triangulating our way to a picture of the structure we inhabit. It is, as I said earlier, like mapping the floor plan of a house while standing in one room in the dark. The spiral arms of the Milky Way that you see in diagrams, those clean, clearly defined curves, are artists' reconstructions based on real data, yes. But they are smoother and more certain-looking than the data itself. The actual picture from the surveys is messier, with arms that are fragmented, kinked, less symmetrical than the ideal. The galaxy is not a perfect Nautilus shell. It is a real, complex, somewhat ragged gravitational structure that has been disturbed by interactions and infalls and internal dynamics for billions of years. The clean diagrams are our best guess, cleaned up for presentation. That honesty is important, not because it should diminish your sense of wonder at the Milky Way, it should not, but because the real galaxy, complicated and uncertain, only partly known, is more interesting than the textbook version, a place still being mapped, home still being understood, and our address in it. The Orion Arm that formally dismissed Spur larger and more substantial than its reputation, is itself an example of how our knowledge deepens over time. The BeSSeL Survey's 2016 measurements were not a minor footnote. They changed where we thought we were. They promoted our neighborhood from side road to something closer to an avenue, and there will be more revisions to come as data from Gaia and from future surveys continues to refine the picture. We are the first generation of humans who have something approaching a real three-dimensional map of the Milky Way's structure. And even so, it is a map with huge blanks, large uncertainties, and regular revisions. We are early in the process of understanding our home. The Sun continues its orbit at 230 kilometers per second, carrying us through the Orion Arm, through the local bubble, 60-some light-years above the midplane, moving in its gentle bob. 20 laps completed, billions of years of orbiting ahead. The arms rotate around it, or rather, the density wave pattern moves through the galaxy while the Sun moves through the wave, a slow trading of positions that never quite keeps the Sun pinned to any particular arm for long. We are passing through, as everything in the galaxy is passing through. The structures are persistent, but the inhabitants of those structures are transient. The arm will outlast this particular passage of the Sun through it. The Sun will return to this region of the galaxy in another galactic year, but the arm may have shifted slightly, and the Sun's position within it will be different. Nothing is fixed. Everything moves. The galaxy is not a painting, it is a process. And that process, stretching over billions of years, has produced structures not just in the disk, but surrounding it. Ancient, glittering relics of the galaxy's formation and its long history of interactions. The halo, the globular clusters, the dark matter envelope that gives the whole system its mass, the cannibal history that built the inner halo from the remnants of a swallowed galaxy. That is where we are going next. Out of the disk above and below the plane, into the older and stranger regions surrounding everything we have described so far. But take a moment here first. In the Orion Arm, in the bubble, 60 light-years above the plane, moving at 230 kilometers per second. The nearest star, a grain of sand 14 kilometers away in the model we have been carrying. The galactic center, the distance of the Earth to the Sun in that same model. The whole disk, the distance to the Moon. The arms glow because stars are being born in them. The bar endures because gravity is patient. The black hole sits at the center, quiet, waiting, 4 million solar masses doing nothing in particular today. The dust that hid all of this from us is still there, but we have learned to see around it. And we, in our spur, in our bubble, on our 21st slow lap, are just starting to understand the scale of the place we have always called home. It is a great deal to hold, no rush. You do not have to hold it all at once. Just let it settle quietly the way the light from the galactic center settled for 26,000 years before reaching us, patient, soft, arriving in its own time. And when you are ready, we will go outward, into the halo, into the dark. So outward then, beyond the disk, beyond the thin plane we have been traveling through, the central bar with its ancient stars, the grand sweeping arms where new suns are born and die, the quiet spur we call home, the bubble of hot emptiness our own stellar ancestors blew around us. Beyond all of that, there is something else, something older, something that surrounds the whole system the way a winter atmosphere surrounds a lit window seen from far away. A presence more felt than seen. We are going into the halo. Picture it this way. Everything we have described so far, the disk, the bar, the arms, the entire flat spinning structure of the Milky Way, is a single glowing coin lying on a vast dark table, thin, brilliant in its own plane, but around that coin in every direction, extending far above it and far below it and out past its edges in a rough, irregular sphere, there is another structure altogether. Not a disk, not a thin plane, a halo, a surrounding cloud of older, dimmer, slower objects. Stars that predate the disk itself, clusters that formed before the spiral arms existed, ancient wanderers moving on orbits that care nothing for the flat rotation of everything beneath them. The halo is not nothing, it is not empty space, it is, in a very real sense, a record. The oldest physical record the Milky Way has kept of its own history, and it is full of stories. Let us begin with the globular clusters. You may have seen photographs of them, and if you have, they stay with you. A dense, spherical swarm of stars, packed tightly at the center and thinning toward the edges, glittering like a city seen from above at night. Every point of light, a sun. They are extraordinary objects, and there are, at last count, more than 150 of them orbiting the Milky Way. More than 150 ancient cities of stars moving through the halo in great looping orbits that pass above and below the disk, some of them taking hundreds of millions of years to complete a single pass. They do not rotate with the disk the way the sun does. They move in all directions, inclined at all angles, as if they existed before the disk decided which way to spin and never bothered to conform. They are very, very old. Some of the globular clusters orbiting the Milky Way contain stars that are more than 13 billion years old. Older than the disk, older than the spiral arms, older, almost, than we can easily say, because the universe itself is only about 13.8 billion years old, and some of these clusters were already forming when the cosmos was less than 1 billion years into its existence. They are not relics, they are witnesses. Whatever the Milky Way was in its earliest years, a turbulent, formless, gas-rich thing, not yet the structured spiral we live in now, these clusters were there. Think of what that means. The light you would receive from a star in a globular cluster, were you somehow standing on a planet inside one, would be the light of a star that formed before the Earth existed by nearly 9 billion years, before the Sun existed, before the solar system's ingredients had even been made by an earlier generation of dying stars. Those stars were already old when ours was born. And the sky, if you lived inside a globular cluster, would be spectacular in a way that has no parallel in our quiet corner of the Orion Arm, where we see a few thousand stars with the naked eye on a clear night. A planet inside a globular cluster's core would see perhaps 1 million. The night sky would never truly go dark. The combined light of so many nearby stars would be enough, not to read by perhaps, but enough to cast faint shadows, enough to feel like permanent twilight. A sky so full of light that darkness would be a theoretical concept, not a nightly experience. It is beautiful to imagine. And it is, as far as we know, real. Those clusters are there, orbiting above and below us right now, carrying their ancient stars in patient elliptical paths through the halo. Now here is where the halo's story takes a turn, because those globular clusters and the ancient stars scattered more loosely through the halo are not all simply native to the Milky Way. Some of them, perhaps many of them, came from somewhere else. And discovering that the way we discovered it and what it tells us is one of the more startling chapters in modern astronomy. The Milky Way, it turns out, is partly made of something it ate. This is not a metaphor. It is, in the technical language of galaxy formation, called a merger event. Galaxies grow by absorbing smaller galaxies, dwarf galaxies, satellite galaxies, companions that wander too close and get pulled apart by gravity, their stars scattered into the host galaxy's structure. This is how large galaxies build themselves over cosmic time. The Milky Way has been doing this for billions of years, but until recently we did not know the scale of what it had consumed. In 2018, two papers, one by Amina Helmi and her colleagues and one by Vasily Belokurov and his colleagues, changed that picture dramatically. Both teams were working with data from the Gaia Space Telescope, ESA's extraordinary survey mission that has been mapping the positions and motions of stars across the Milky Way with unprecedented precision. And what Gaia revealed when you looked at the stars of the inner halo was something unexpected. A large population of stars moving on very elongated radial orbits, diving in toward the galactic center and swinging back out again rather than circling smoothly the way the disk's stars do. Orbits that told a story of stars that had once belonged to something else, something that fell in and was torn apart, its stars flung into orbits that still carry the memory of the collision. The two teams reached similar conclusions by slightly different routes. What they had found were the remnants of a substantial dwarf galaxy, a companion the Milky Way had absorbed sometime between roughly 8 and 11 billion years ago. Helmi and colleagues called it Gaia Enceladus, after the mythological giant buried beneath a mountain. Belokurov and colleagues called it the Gaia sausage, because of the distinctive sausage-like shape the star's velocities make when you plot them a certain way in a diagram, a stretched, elongated cloud that only makes sense if those stars once fell straight in and out, over and over, along radial paths, both names stuck in different contexts. In the technical literature, you will often see it written as Gaia Enceladus sausage, but whatever you call it, the discovery was profound. This was not a small event. The galaxy the Milky Way absorbed was not a tiny dwarf galaxy. It was a substantial system, estimated to have had a mass somewhere in the range that would have made it a significant companion, its merger enough to heat up and distort the inner halo in ways that are still visible in the stellar motions today. The stars of Gaia Enceladus now make up a large fraction of the inner halo. Some of the globular clusters in the halo may have originally been this galaxy's own clusters, brought along for the journey and absorbed along with everything else. Think of that. Some of the oldest stellar cities orbiting the Milky Way may not have formed here at all. They may be immigrants, captives of a collision that happened before the Earth existed, and they are, now, simply ours, or ours and theirs together, the boundary dissolved by 9 billion years of shared orbit. The Milky Way is a cannibal, and in eating what it ate, it became more than it was. This is, in fact, how galaxies work. The Milky Way has absorbed many smaller systems over its history, and it will absorb more. The Sagittarius dwarf galaxy, the same one whose gravitational interactions help produce the disk's warp and flare, is currently being shredded. Its stars are being stretched into long streams that wrap around the Milky Way multiple times. Some of its stars are already mixed into our halo. The Magellanic Clouds, the two irregular dwarf galaxies visible from the southern hemisphere as faint, misty patches, are also in the Milky Way's gravity well, slowly destined for absorption in the distant future. The Milky Way grows. Slowly, over billions of years, it pulls in what surrounds it and adds it to itself. The halo is the archive of those meals, still visible in the kinematics of stars that remember where they came from, even if the galaxy they came from no longer exists. But the stellar halo, the visible stars, the globular clusters, the ancient wanderers, even the absorbed remnants of Gaia Enceladus, is not the whole story of what surrounds us. Not even close. Because most of the Milky Way is invisible. This is something worth sitting with for a moment, in the quiet, wherever you are. The galaxy you have been picturing through this entire journey. The brilliant central core, the glowing bar, the spiral arms blue-white with newborn stars, the thin flat disk, even the ancient stellar halo. All of that, everything that emits or reflects or absorbs light, everything we can detect directly with any telescope ever built is a minority. A small minority, perhaps 10 to 15% of the Milky Way's total mass. The rest is dark matter. Dark matter is one of those phrases that can start to feel like jargon if you hear it too many times. So let us be precise about what it means and what it does not mean. It does not mean we simply have not found it yet, the way you might not have found your keys. It means we have excellent, overwhelming evidence that something is there. From the way stars and gas move, from the way the galaxy holds together against the forces that should fling it apart, from the way the rotation speed of the disk behaves in ways that the visible mass alone cannot explain. And yet, whatever that something is, it does not interact with light. It does not emit it, absorb it, or reflect it. It is, from the perspective of every electromagnetic telescope ever pointed at the sky, perfectly transparent, perfectly invisible. The dark matter halo surrounding the Milky Way extends far beyond the stellar disk, far beyond the stellar halo, out to perhaps 600,000 light-years or more from the galactic center, 6 times the diameter of the visible stellar disk, a vast invisible sphere roughly spherical in shape within which the visible galaxy sits like a lit lantern inside a room we cannot see. And it is heavy. The total mass of the Milky Way, including dark matter, is estimated at roughly 1 to 1.5 trillion solar masses. The visible stars, all 100 billion or 200 billion of them, account for perhaps a tenth of that, maybe less. The dark matter is the overwhelmingly dominant component. The galaxy you see in the night sky, the band of light stretching overhead, is the glint of a flame burning inside a structure mostly made of something we cannot name. In our grain of sand model, the one where the Sun is a 0.5 millimeter grain, and Proxima Centauri is another grain 14 kilometers away, the dark matter halo would extend to something like 2 million kilometers from the center of our model galaxy. Bigger than the Earth-Moon distance by 6 times, an invisible sphere containing everything we have described, and itself containing nothing we can directly see. Just a gravitational presence, enormous and quiet, holding the whole system together. We know dark matter is there because without it, the galaxy does not work. The stars in the outer disk of the Milky Way move too fast. If the only mass present were the visible mass, the stars and gas and dust we can detect, then the gravity holding the outer disk together would be insufficient, and the stars there should be moving more slowly, the way planets in the outer solar system move more slowly than inner ones. They do not. The rotation curve of the galaxy is flat, meaning stars at all radii move at roughly the same speed, which can only be explained if there is additional, unseen mass distributed in a large halo around the disk. This observation holds for galaxy after galaxy across the universe. It is not a Milky Way peculiarity. It is a feature of how galaxies work, first noticed by astronomer Vera Rubin and colleagues in detailed studies of galactic rotation in the 1970s, and the conclusion that follows from it that most of the mass in the universe is made of something we have never directly detected is one of the most unsettling and intellectually honest results in all of science. We do not know what dark matter is. There are candidates, classes of hypothetical particles with the right properties to explain the observations, but none have been confirmed by direct detection. The dark matter halo is, for now, a fact without a face, a presence detected entirely by its gravitational effect, the way you might know someone is in a dark room not by seeing them, but by the way the objects around you have moved. So here is the Milky Way, as it actually is, not as it usually appears in diagrams. A thin, brilliant disk of visible matter, stars, gas, dust, embedded inside a stellar halo of ancient stars and globular clusters, itself embedded inside a dark matter halo perhaps 12 times its diameter. The thing we call the galaxy, the thing whose center we have been trying to reach and whose edge we have been trying to find, is not even the majority of what is here. It is the lit part of something much larger and stranger, and within the lit part we have still only counted a fraction of the stars. Let us talk about the stars. How many are there, and how confident can we be? The number you hear most often is something like 100 billion. 100 billion stars. It sounds precise. It sounds like we counted them. We did not. The true picture is, characteristically for this galaxy, a great deal more uncertain and a great deal more interesting. The current best estimates for the total number of stars in the Milky Way range from roughly 100 billion to 400 billion. Not 100 billion plus or minus 10%. 100 to 400 billion. A range of a factor of 4. That is not a small error bar, that is an enormous one, and the reason for it tells you something important about the galaxy itself. Most of the stars in the Milky Way are red dwarfs, M-type stars, M-dwarfs, small, dim, slow-burning stars with a fraction of the Sun's mass and a tiny fraction of its luminosity. They are the most common type of star in the galaxy by a wide margin. Surveys suggest they make up something like 70 to 75% of all stars. 3 out of every 4 stars in the Milky Way is a red dwarf, and individually, they are almost impossible to count. A red dwarf, even a few hundred light-years away, is too dim to see without a telescope. Most of them across the galaxy are simply invisible from where we stand, not obscured by dust, just intrinsically too faint to detect at galactic distances with current instruments. We can estimate their total number from the ones we can see nearby, combined with models of how stellar populations work, but we cannot survey them directly the way we can survey brighter stars. So when someone says 100 billion stars, what they mean is something like 100 billion is a defensible lower bound based on more luminous stars we can count or reliably trace. But when you add in all the red dwarfs we cannot directly see, the number could reasonably rise to 200 billion or more. Some estimates, depending on how you model the faint end of the stellar mass function, go higher still to 300 or 400 billion. The honest answer is, we do not know. The true star count is uncertain, and the uncertainty is driven by the very commonness of the galaxy's most common stars. We are uncertain not because the galaxy is exotic, but because its most typical inhabitants are just too dim to count. This is worth thinking about for a moment. The sun, your sun, the warm thing that rises each morning and drives every biological process on Earth, is not a typical star. It is above average, larger than most, brighter than most, longer lived in some respects than the very small. In a galaxy where the typical star is a dim red ember, barely a tenth the mass of the Sun, burning quietly for potentially hundreds of billions of years, the Sun is something of an outlier on the bright side. Most stars are less than the Sun, and most of the life histories possible in this galaxy, if there are any, are probably lived under the light of red dwarfs rather than yellow ones. Now consider the Gaia mission. ESA's Gaia Space Telescope has been, since 2013, building the most precise and comprehensive map of the Milky Way ever assembled. Its third data release, Gaia DR3, contains precise positions, distances, and velocities for approximately 1.8 billion stars. 1.8 billion. A number large enough that if you tried to count them one per second, it would take you more than 57 years. And yet, 1.8 billion is, at most, 1 to 2% of even the lower estimate of the total stellar population, less than 2 stars in every 100. If the true total is 300 billion, Gaia has counted less than 1 star in 160. We have the most detailed stellar catalogue in human history, and it covers a rounding error of our own home. This is not a criticism of Gaia. Gaia is a staggering achievement, but it illustrates the scale of the problem and of the galaxy. The Milky Way is so vast and its most common stars so faint that even an extraordinary instrument working for years, measuring 1 billion+ stars, has barely scratched the surface of the whole count. The galaxy is not a closed book we are reading. It is a library, and we have opened a few pages. There is something quietly remarkable about knowing this, that we live here, in this vast and only partially known system, and that we are aware of our own ignorance of it. The Milky Way is not a thing we have fully measured and understood and filed away. It is an ongoing project. Every new data release from Gaia, every new survey in infrared or radio, adds a little more to what we know and frequently reveals something we had wrong. The bar's shape was revised. The local arm's status was revised. The halo's origin was revised. The galaxy is being understood in real time by generations of people who will never finish the work. And at the edge of that work, and at the boundary of what we can currently see with any instrument, things begin to fade. There is no last star, not in the way the phrase suggests, no single outermost sun sitting at a definable border with a sign that says, "The galaxy ends here." The stellar density of the disk does not drop to 0 at some radius and then remain 0. It falls off exponentially, gradually, the way a light fades with distance rather than the way a door closes. You do not cross a boundary into empty space. You move through thinner and thinner territory until you cannot say with confidence whether a given star is part of the Milky Way or simply adrift in the intergalactic void. The outer disk warps. We mentioned this briefly, but it deserves a moment of description. The Milky Way's disk is not a perfectly flat plane. Beyond a certain radius, it bends, curving upward on one side and downward on the other, like the brim of a hat that has been sat on, or the subtle flex of a large, thin plate. This warp and flare of the outer disk has been mapped in detail using Gaia data from around 2020, and the picture that emerged is of a disk that becomes progressively more distorted as you move outward, thicker and bent, the clean geometry of the inner disk giving way to something more irregular. The cause of this warp is not fully settled. The leading explanation involves gravitational interactions with satellite galaxies, the Sagittarius dwarf galaxy on one side, the Magellanic Clouds on the other, both tugging at the outer disk's edges over billions of years. Gravity is patient, and even a gentle tug repeated over long enough timescales bends things. The warp you see in Gaia's data is the accumulated result of those interactions, a physical mark left on the disk by the galaxy's smaller neighbors. And in the halo, beyond the disk, stars exist at very large distances from the center. There are populations of stars, specifically types called RR Lyrae variables and distant red giants, that serve as traces of the outer halo. These are stars whose intrinsic luminosity is known or can be inferred, which makes it possible to calculate their distance from how bright they appear to us. Some of them have been found at distances exceeding 1 million light-years from the galactic center. 1 million light-years, 10 times the diameter of the disk. At that distance, calling a star part of the Milky Way starts to feel like a question of definition as much as measurement. The halo extends so far that the outermost stars in it exist in a region that is, in a real sense, neither clearly within our galaxy nor clearly outside it. The boundary of the Milky Way is not a place, it is a gradient, a slow, uncertain dissolution of belonging, and to travel across it, to traverse from the galactic center to the last faint red giant drifting in the outer halo, would require, at the speed the sun moves through the galaxy, something on the order of tens of billions of years. Far more than the sun has left to live. Far more than the galaxy itself has existed. The journey from the center to the edge, in any physically meaningful sense, is one no physical traveler ever completes. At the speed of light, the fastest anything can travel, the limit the universe imposes on information and matter alike. Crossing the disk takes 100,000 years. Reaching an outer halo star takes 1 million. And the Sun travels at roughly 230 kilometers per second, 1/12,000th of light speed, which is astonishing by any terrestrial measure and still laughably slow against galactic distances. At that pace, covering a single light year takes just over 13,000 years. The nearest star, 4.2 light years away, is a journey of some 58,000 years. The center, 26,000 light-years distant, would take roughly 340 million years to reach. The journey to the last star is only completable in imagination, in scale models, in the patient work of telescopes and computers, and people who sit in darkened rooms turning data into understanding. The Milky Way is not a place we can go, it is a place we can only know from the inside, looking out, building our picture from what light and gravity tell us, and that too is worth holding gently. We have never seen this place from outside. No spacecraft we have ever built will leave the Milky Way in any time scale that matters to civilization. The distances are simply too vast, the journeys too long. The Voyager probes, moving at something like 17 kilometers per second, have traveled about 23 billion kilometers from the Sun in the roughly 47 years since their launch. And that sounds far. In light years, it is about 8/10,000ths of a light year. At that pace, it would take more than 70,000 years just to reach Proxima Centauri, 4 light years away. And the galaxy's edge is 25,000 times farther than that. We are, in a very practical and permanent sense, inside. We have always been inside. Every image of the Milky Way you have ever seen labeled as a photograph of our galaxy, the beautiful face-on spiral with the glowing core and the blue-white arms, is either another galaxy, most commonly Andromeda, or a galaxy like NGC 6744, chosen for its resemblance to our own, or it is an artist's reconstruction, assembled from the internal data Gaia and other telescopes have gathered and rendered into a picture of what we believe our home looks like from a vantage point we will never actually occupy. We are drawing a map of our house from the inside, with no windows, using only the sounds the walls make. And yet we know so much. That is the remarkable thing. We know where we are, in the Orion Arm, 26,000 light-years from the center, 60 light-years above the plane, inside a local bubble blown by ancient supernovae, moving at 230 kilometers per second on our 21st slow lap. We know what is at the center, a supermassive black hole 4 million times the Sun's mass, patient and mostly quiet, its shadow photographed for the first time only in 2022. We know the shape of the disk, the structure of the bar, the nature of the arms as density waves where stars are born and die. We know the halo is ancient and partly cannibalized. We know the dark matter is there, enormous and invisible, holding the whole structure together. We know the edge is a fade, not a wall, and that stars drift in the outer halo at distances greater than 1 million light-years. We know all of this, and we have never left. There is something in that which takes a long time to fully appreciate. The galaxy is so large that standing inside it is more like standing inside a continent than standing inside a room. You cannot see all of it from any one place. You build the picture slowly from 1,000 different measurements, each one a small window onto a corner of the whole. And slowly, across generations of astronomers and decades of missions and terabytes of data, the picture assembles itself. Not perfectly, not completely, but recognizably, with real detail and real confidence and real humility about what remains unknown. The Milky Way contains somewhere between 100 and 400 billion stars. We have measured the orbits of 1.5 billion of them. The rest are known to us only statistically, by inference, by the way their aggregate mass shapes the rotation of the disk and the motion of the halo. We know they are there the way you know a crowd is present in a darkened stadium, not by seeing each face, but by the sound and the heat and the way the structure holds its shape. Most of those stars are dim and red, burning slowly in the dark, individually invisible at galactic distances, but collectively enormous in their numbers. Most of the galaxy's total mass is not stars at all, but dark matter, invisible and unnamed. Most of what we will ever know about our home we have learned in the last few decades, and most of what there is to know we have not yet begun to understand. The Milky Way is large, it is old, it is mostly empty, mostly dark, mostly unknown, and it is, in every atom you are made of, home. Take a breath wherever you are. We have come a long way tonight. From the grain of sand on your fingertip to the black hole 4 million times the Sun's mass, smaller than the orbit of Mercury, sitting at the center of everything we will ever see. We have moved through the bar, the spiral arms, the density waves where stars are being born right now while you listen, and we have settled for a moment in the Orion Arm, 60 light-years above the plane, inside a bubble of hot gas, moving at 230 kilometers per second through a galaxy we are only beginning to understand. Then we went outward, into the halo, where globular clusters older than the Earth orbit in arcs that care nothing for the disk's rotation. Clusters that were already ancient when the Sun was born, carrying stars that formed when the universe was less than 1 billion years old. We found the memory of a swallowed galaxy, Gaia Enceladus, the Gaia sausage, absorbed 8 to 11 billion years ago, its stars still traceable in the inner halo's distinctive elongated orbits, a ghost written in kinematics, visible now because of what Gaia revealed and what Amina Helmi and Vasily Belokurov and their colleagues recognized in the data. The Milky Way ate something, and in eating it, became more of itself. We found the dark matter halo extending to perhaps 600,000 light-years, invisible and enormous, accounting for 85 to 90% of the galaxy's mass. 1 trillion solar masses or more of something we cannot name, holding the whole luminous system inside it the way water holds a snowflake. The disk is real and bright and beautiful, but it is a small fraction of what is there. We found the stars impossible to count precisely because the most common ones are the dimmest ones, too faint to survey across galactic distances, their total number somewhere between 100 billion and 400 billion, depending on how you model what you cannot see. Gaia has measured 1.8 billion of them. Extraordinary, unprecedented, and still less than 2% of the whole. We live in a galaxy we have, in a real sense, barely counted, and we found the edge, or rather found that the edge is not a place. The stellar density fades, the disk warps and flares at the margins, bent by the gravity of satellite galaxies that are themselves slowly being consumed. Stars drift in the outer halo at distances greater than 1 million light-years, farther from the center than Andromeda is from us, almost. And they are technically still part of the Milky Way, except that calling them so is more a question of orbital mechanics than of neighborhood. The galaxy dissolves, it does not end. And the journey to the last star, the thought experiment this whole night has been built around, turns out to be one that can only ever be completed in the mind. Not in any spacecraft, not in any human lifetime or civilization's lifetime. The scale is too large, the speeds available to us too small. The galaxy keeps us inside it, not as a prison but as a home so large that the concept of exploring it entirely has no practical meaning. What we can do is what we have been doing tonight. We can think it, we can model it, we can shrink it to the size of something holdable, 2 grains of sand separated by 14 kilometers of nothing. and feel, in that image, the truth of it, the emptiness, the scale, the improbable fact that the galaxy contains 100 billion or more stars and is, at the level of the individual star, almost entirely vacant. 2 grains of sand, 14 kilometers, nothing in between. And in the morning, when it is day again, and the galaxy is still there overhead, hidden by the blue atmosphere and the scattered light of the sun, that image will still be accurate. The nearest star will still be 14 kilometers away in the model. The galactic center will still be 26,000 light-years away, its light having left before the last ice age's peak, arriving now, patient and old, to land on telescopes and detectors, and eventually on the minds of people who built machines specifically to catch it. One more thing gently. In about 4.5 billion years, the Milky Way and Andromeda will merge. Andromeda, M31, the nearest large galaxy, 2.5 million light-years away, approaching us at about 110 kilometers per second, will eventually collide with the Milky Way in a long, slow gravitational dance that will take billions of years to complete, the 2 systems passing through each other, their spiral arms distorted and flung into vast tidal streamers, their stars scattered into new orbits, their black holes eventually sinking toward each other at the centers of the merged system. The result, billions of years from now, will be a new galaxy, sometimes called Milkomeda. Probably an elliptical galaxy, less structured than either of its parents, a great golden cloud of stars rather than a spiral, the spiral arms long since dissolved. This is not something to worry about, it is something to appreciate. The cosmos operates on timescales that make human history look like a rounding error, and the Andromeda merger is so far in the future that the Sun itself will have grown old and expanded into a red giant long before the collision is complete. But the fact that it is coming, that even our galaxy, vast and ancient and seemingly permanent, is part of an ongoing story of collision and merger and transformation, says something quietly important about the nature of things. Nothing is final. Everything is in motion. The galaxy that contains everything you have ever known is itself moving through something larger, toward a future it will not survive in its current form, and something new will come from it. That is not sad. It is, in a strange way, comforting. The universe does not stop. It transforms. And you tonight, wherever you are, lying in the dark, or almost there, the soft edge of sleep somewhere near, you are made of this. Every atom in you was forged in a stellar interior, in the core of a star that lived and died long before the sun was born, scattered into the interstellar medium, gathered up again in the cloud that became the solar system, built into planets and oceans, and eventually into the particular arrangement of matter that is you, right now, listening to this. You are galactic material. You are 100 billion solar masses, give or take, compressed into something that fits in a bed. The galaxy is not out there, separate from you, a thing you are looking at from a distance. You came from it. You are one of its product, or one of the things that happens when you give 100 billion stars and 4 billion years, and the right chemistry, enough time. The universe made you the way it makes everything, slowly, accidentally, beautifully, from the inside out. Back at the beginning of tonight, I asked where you are in the world, what corner of the planet you are in, what the time is where you are listening, whether you have a lamp still on, or whether the dark is already complete around you. I meant it then, and I mean it now, more than ever. Because wherever you are, the Milky Way is there too. Above you, even in the daytime when you cannot see it, even in the city where the light washes it out, even when clouds cover it. 26,000 light-years of galaxy stretching out from where you lie, the galactic center in the direction of Sagittarius, the thin disk crossing the sky as that faint, pale band we have been walking through all night, the halo extending in every direction out to distances you now have a model for, the dark matter halo enclosing all of it, enormous and quiet, and you, a grain of sand's worth of matter on a grain of sand of a planet in a quiet spur, above the plane, inside a bubble.
On the 21st lap, the center of your own experience of it all. That is a remarkable place to be. It is the only place any of us has ever been.
If you enjoyed this slow journey tonight, a gentle like and subscribe means more than you might think. Small creators like me really rely on your support to keep these going, and it helps more people find their way here. And if you feel like leaving something in the comments, I would love to know where in the world you are listening from and what time it is in your corner of the night. Wherever you are, I hope something in this felt vast and quiet and somehow, improbably, close. Close the books, dim the lamp, class is over, sleepy scholar.